In the previous module, we talked in details about the Maxwell-Boltzmann statistics, and we also derived the Maxwell-Boltzmann distribution law. Maxwell-Boltzmann statistics, as you know, is also called classical statistics. In this, the particles are distinguishable from each other and there is no restriction on the occupancy of energy levels. Further, here we also do not take into account the internal structure of the particles. Today we will talk in detail about quantum statistics. There are two types of quantum statistics. One is the Bose-Einstein statistics and second is the Fermi-Dirac statistics. For both these statistics, we will derive the corresponding distribution laws. In the Bose-Einstein statistics, we deal with the particles and take into consideration their internal structure. This is a big difference from the earlier Maxwell-Boltzmann statistics. Secondly, particles in the Bose-Einstein statistics are considered indistinguishable from each other, and also there is no restriction on the occupancy of the energy levels. Further, one may ask that which type of particles will obey Bose-Einstein statistics. It has been found that the particles which have integral spin such as photons, they obey Bose-Einstein statistics, and these spin can be calculated once we know their internal structure. On the other hand, in Fermi-Dirac statistics, which we will also study today, we also take into account the internal structure of the particles, but here the particles, unlike the Bose-Einstein statistics, they have half integral spin like electrons. So, if there is a collection of electrons, they will obey Fermi-Dirac statistics. These particles are also indistinguishable from each other and there is here restriction on the occupancy of energy levels. Please note, this is very important. In Bose-Einstein statistics, there is no restriction, but in Fermi-Dirac statistics, which is obeyed by half integral spin particles, there is a restriction on the occupancy of energy levels. Let us now first derive the Bose-Einstein distribution law. To derive the Bose-Einstein distribution law, basically we mean by deriving the Bose-Einstein distribution law means we have to find out what distribution will give W the maximum value. That means, what value of Ni will make the maximum number of microstates possible for such a system. Here we start with a system which contains n particles which obey Bose-Einstein statistics and the total energy of the system is E, and let the whole system be at temperature T. Now, as we have already learned earlier also, if Ni is the number of particles occupying ith energy level with energy epsilon I, and then we can see that the following two conditions must be satisfied. First is equation 1, which gives the expression for total energy, and that is equal to summation Ni epsilon I, and second is capital N, which is equal to summation I N I. Now, as you have already learned earlier that the value of W, that means the number of microstates associated with any macrostate in the case of Bose-Einstein statistics is given by the expression. This is WBE is equal to pi I, that is the capital pi I, which is equal to Gi plus Ni minus 1 factorial divided by Ni factorial, then Gi minus 1 factorial. Here Gi is the degeneracy of the ith energy level. Ni is the number of particles in the ith state, and W, as you already know, is the number of microstates associated with the macrostate, and we also call it a thermodynamic probability. One thing which you should notice from this equation is that if the levels were non-degenerate, that means Gi is equal to 1, then in that case WBE, as you can see here, will reduce to 1. That means there will be no microstate, that means only one microstate associated with any macrostate. So, in this case the number of microstates arise primarily because of the degeneracy of the energy levels. So, degeneracy plays a very important role in Bose-Einstein statistics, and later on we will see it also plays a very important role in Fermi-Dirac statistics. And generally in the case of Bose-Einstein statistics, we assume that degeneracy is much larger than 1. Let us take one example. Suppose Ni is equal to 1 and the degeneracy for this level Gi is equal to 2, then the WBE just for this level will become equal to 2. That means there are two ways in which the distribution of the given particle can be achieved in the two specified states given by the Gi value. Now, since in the Bose-Einstein statistics generally Gi is much greater than 1, therefore, the expression for W can be simplified and it can be written as it is shown in equation 5. WB is equal to pi I is equal to Gi plus Ni factorial divided by Ni factorial Gi factorial. We have neglected 1 in comparison to the rest of the terms because Gi is much larger than 1. Now, if we have to find out the value of Ni which will make WBE maximum, we will proceed exactly in the similar way as we have done in the case of Maxwell-Boltzmann statistics. First thing which we do is we take logarithm on both sides, but before doing that we have already done it in our Maxwell-Boltzmann statistics, and that is that dE will come out to be equal to 0, and that will make summation Ni d epsilon I is equal to 0. That is basically equation 8 as we have seen here. And then there is equation 7 which come once we take the differential of n, capital N, dn becomes 0, and that is summation I dni is equal to 0. So, these two equations were there in our Maxwell-Boltzmann statistics as well. Now, we take the logarithm of the expression for WBE, and this gives us equation 10, which is ln WBE is equal to summation I ln Gi plus Ni factorial minus summation I Ni factorial minus summation I Gi factorial. Here also we now apply the Stirling approximation which we have learnt already, and once we use the Stirling approximation, this equation gets modified and we get the following relation as it is shown here. Ln WB is equal to summation I Gi plus Ni ln Gi plus Ni minus Gi plus Ni parenthesis closed minus summation I Ni ln Ni minus Ni minus summation I Gi ln Gi minus Gi. This equation has come after applying the Stirling approximation. This equation on simplification gives us the equation as you can see here. This gives ln WBE is equal to summation I Gi plus Ni ln Gi plus Ni minus summation I Ni ln Ni minus summation I Gi ln Gi, and that is equation 14. So, this we have obtained by applying Stirling approximation, and of course, initially we took logarithm. Now, we apply the first condition of maxima, and that is d ln w should be equal to 0, and if we apply this condition as we have done it here, we get ultimately d ln w b e is equal to summation I ln g I plus n I upon n I, and d n I is equal to 0, or in other words, summation I ln g I plus n I upon n I into d n I is equal to 0. This is the third equation, equation number 14, which we get. So, in all we have 3 equations now, as we had in the case of Maxwell-Boltzmann statistics. First is summation I d n I is equal to 0, second is summation epsilon I d n I is equal to 0, that is equation 9, and then summation I ln g I plus n I divided by n I into d n I is equal to 0, that is equation 14. Now, again these 3 are independent equations, each one of them equal to 0. They can be combined for a given system using Lagrange's method of undetermined multipliers. We multiply one equation by alpha, other with beta, as we did it earlier in the last module, and we get the corresponding equation summation I is equal to alpha plus beta epsilon I ln g I plus n I upon n I parenthesis close d n I is equal to 0. And in this equation we can notice that alpha plus beta epsilon I plus ln g I plus n I upon n I would be equal to 0 for each value of I. And if we simplify it, one gets the following expression, which is n I is equal to g I divided by e to the power minus alpha plus beta epsilon I minus 1, that is equation 15. So, this equation gives us the Bose-Einstein distribution law. Although alpha and beta are still unknown, but as we will see later on, here also beta will come out to be equal minus 1 upon k T, and similarly alpha we will show this also is the corresponding partition function. And this Bose-Einstein distribution law gives us the value of n I, which when substituted in the expression for W b E will make W b E maximum. That means, it gives the value for the most probable macro state for Bose-Einstein statistics. After having derived Bose-Einstein distribution law, exactly on similar lines one can go ahead for Fermi-Dirac distribution law. Here also the total E and total N, they are constant, and they are given by the expression E is equal to summation I n I epsilon I, and capital N is equal to summation I n I. The value of the W for Fermi-Dirac statistics, as we have already learned in our second module, that is given by W f d is equal to pi I g I factorial divided by n I factorial g I minus n I factorial. This is the equation 18. Here also, as you will notice here, that the degeneracy will play a very important role, and one can see that for getting a meaningful value of W f d, g I should be greater than n I, because if g I is greater than n I, then W f d would be greater than 1. However, if g I is equal to n I, as you can see from expression 18, this whole expression will reduce to 1. That means, just one microstate for every macrostate. So, here also the degeneracy is going to play a very important role. Here also we need to find out that value of n I, which when substituted in the expression for W f d will make W f d maximum. We take the differentials of the two equations. First equation, as we derived it earlier, is equation 20, which is summation I d n I is equal to 0, and second which comes from the constant value of energy, and that is summation I n I d epsilon I is equal to 0. This ultimately will give us the equation summation I epsilon I d n I is equal to 0. Exactly on the similar lines, now we take the logarithm of WFD. So, if we do that, we get ln Fd is equal to ln summation I ln gi factorial minus summation I ni factorial minus summation I gi minus ni factorial, that is equation third. We simplify it further by applying once again Stirling approximation, and using simplifying it we get the expression which you can see is that ln WFD is equal to summation I gi ln gi minus gi parenthesis closed minus summation I ni ln ni minus ni parenthesis closed minus summation I gi minus ni ln gi minus ni minus gi minus ni parenthesis closed. And if we apply the first condition of maxima here once again, then the first differential should be 0, and once we do that, as we are doing it here, you can see d ln WFD, and if we simplify it further, ultimately we get the equation 27, which comes from the fact that d ln W comes to be equal to summation I ln gi minus ni upon ni d ni is equal to 0, or in other words summation I ln gi minus ni upon ni d ni is equal to 0. So, once again we have these three equations. First equation comes from the constant value of n. Second equation comes, which is 22nd, that comes from the constant value of E, and the third, which is 27, that equation comes from applying the first condition of maxima. That means the first differential is taken to be equal to 0. And if we have these three independent equations, applying the method of Lagrange's method of undetermined multipliers, and we combine these three equations, we get ultimately, as we have done it earlier, it comes to be alpha plus beta epsilon I plus ln gi minus ni upon ni is equal to 0 for each value of I. And this on simplification gives us ni is equal to gi upon e to the power minus alpha plus beta epsilon I plus 1, and that is the equation 28, and this gives us what is known as the Fermi-Dirac distribution law. That means, this value of ni which we get from equation 28, if this is substituted in the expression for WFD, then it will make WFD more maximum, and hence it will be the most probable macro state for Fermi-Dirac statistics. As here also we can show, beta will come out to be minus 1 upon kT, and alpha is nothing else but the partition function. So, in this module we have gone into the details of quantum statistics. Quantum statistics basically deals with those particles where we take into account the internal structure. There are two types of quantum statistics. One is the Bose-Einstein statistics, which is applicable to integral spin particles, and second is the Fermi-Dirac statistics, which is applicable to half integral particles. In the case of Bose-Einstein statistics, there is no restriction on the occupancy, whereas in the case of Fermi-Dirac statistics, there is a restriction on the occupancy. And for both of these statistics, we have derived the corresponding distribution laws, which will give us the maximum value of W. For Bose-Einstein distribution statistics, this law gives ni is equal to gi e to the power minus alpha plus beta epsilon I minus 1. whereas for Fermi-Dirac statistics, Ni comes to be equal to Gi upon e to the power minus alpha plus beta epsilon I plus 1. If you examine them closely, in Bose-Einstein statistics, in the denominator there is a minus sign, minus 1, whereas in the Fermi-Dirac statistics it is the plus sign. So, that is very easy to remember also. So, now we have learned about the distribution laws for all these three statistics. Now, our next is how to calculate the macroscopic properties for the bulk system, and this we will do for Maxwell-Boltzmann statistics in our next module.